Optimizing cycle inventory in production settings, the POQ model. When we considered cycled inventory in the case of delivery, and we had quantity Q delivered, the peak inventory was Q, the average inventory was half of Q, and we were just given the flow rate and the rate, which is the rate of consumption, and the pattern of inventory looked like this, where this was the cycle time and Q was the order quantity. When quantity Q is produced, however, and the production is not instantaneous, but it's a given production rate, right? So we are given here two parameters, flow rate, the consumption rate, and the production rate, which must be at least as high as flow rate and typically much higher than the flow rate if we have production in batches. In this case, the peak inventory will not reach Q. So if you order a quantity Q, notice that if the production takes a certain time, so let's look at this part. Production takes a certain part of the cycle. While you're producing quantity Q, you're also going to consume, right, part of that quantity. And therefore, you will not reach a peak inventory of Q, but you will reach a slightly lower inventory level, or depending on the production rate and the flow rate, right? So if production rate is actually very high, much higher than the consumption rate, this fraction will be very small, and then the peak inventory will be close to Q. It will be close to Q times 1 minus some very tiny value, right? However, if the production rate is not much larger than the consumption rate, this peak inventory will be significantly lower, like shown in this picture. And because of this, average inventory will also be smaller. Average inventory, which was said before, really it was peak inventory over 2, Q over 2. Now peak inventory is this decreased quantity, and then you have to divide it by 2 to get average inventory, right? So you will see that we are going to have less of a holding cost in this setting just because of the fact that production takes some time and the inventory buildup does not reach the same peak value. So one thing to be clear is that during the production cycle, the part of the production within the cycle of inventory, we are producing and consuming, right, or depleting inventory at the same time. So that means the rate here of increase in inventory will be P minus R. It will be production rate minus demand rate. Whereas when we deplete the inventory, the rate will be minus R, right? So it will be decreasing by the consumption rate. So similarly to the EOQ model, economic order quantity model, which considers delivered quantity, we can define a model which is called typically in the literature POQ, production order quantity. It is still the lowest cost quantity, right? So the quantity that will minimize cost. But in addition to the parameters we had before, the flow rate, the fixed cost per order, holding cost, the order quantity that we decide, we also have P production rate in units per unit of time. And as before, make sure the same time unit is used, in this case, in 3 measures: flow rate, production rate, and holding cost. Right? They are all expressed per unit of time, and so you have to make sure this is the same unit of time before you start calculations. So again, we're minimizing total cost, and the total cost will be composed of ordering and holding costs, all of them per unit of time. But this case, right, ordering cost is the same, but holding cost is for an adjusted average inventory. And remember, average inventory is Q times this factor, 1 minus R over P divided by 2. So this is now the average inventory, and this is multiplied by H, right? So if you solve this problem similarly as we solved for the EOQ, you will find an optimal order quantity Q star, which differs from the previous solution just by, again, having this factor in the denominator in addition to H. If you recall, before the EOQ model, it was 2KR over H, and the square root. And now it's 2kr over h, but the h is also multiplied in the denominator by this factor 1 minus r over p. And of course, if p is much larger than r, then this factor becomes close to 0, so it stops playing any important role, and you can actually use the POQ model as an approximation of the production order quantity model. So in the previous topic, when we considered batch production, we actually focused on setup time, but now in the production settings, we're focusing on the setup cost. On one hand, setup cost calls for calculating optimal quantity using the POQ model, so the quantity that minimizes the total cost of ordering and holding. On the other hand, setup time calls for adjusting batch size such that we obtain the required flow rate. If you recall, we don't want the system to become a bottleneck, but on the other hand, we don't want too much inventory. So if you think about it, both of those models tell us what quantity to choose. In the context of this topic, we're talking about quantity Q or Q star. In the context of batch production, we call the quantity B, batch size. And but both of them denote basically the same quantity, whether you call it a batch or an order. It's the same quantity we're thinking about here. Which one should we use then? Well, the advice is the following. If you have the costs of ordering and holding, and you can try and optimize them by using the POQ model, so finding the quantity Q star using the POQ model. And if you now assume the batch size B is equal to the Q star, and you find out it is not a bottleneck, then you can set the batch size to B equals Q star. And by that, you basically satisfy both requirements, meaning that you're minimizing the costs of holding and ordering, and at the same time, this process, this step of the process is not a bottleneck, so it is not preventing us from like collecting additional revenue. However, if setting B to the to this value Q star makes the process step bottleneck, then we might want to, of course, decide to set B to a larger value such that it no longer is a bottleneck. The reason for this is, of course, that the optimization of costs are in the POQ model are at the local level. So they consider just the local holding and local ordering cost or batch setup costs in this case, of production setup costs. However, these are usually much smaller than the implications for the overall process. And if you create a bottleneck by setting batch size to a too small value, then you will be perhaps losing some revenue, potential revenue that you could otherwise collect if you had a higher production rate, right? That is now lowered due to the size of the batch that you're using. So in that case, it makes a lot of sense to increase batch size, even though it is higher than the quantity Q star from the POQ model, but it is worth it usually because the potential revenue and the additional profit that we will collect due to increased process capacity often much more than justifies the increase in the local holding or ordering costs. And finally, even in this case, when the step is not a bottleneck, you might also sometimes go for a smaller batch size because of the overall principle that I'm trying to tell you about throughout this course is that higher inventory is always unadvisable. It is always a good idea to work, if possible, with smaller inventories for many reasons, basically, which will lead us eventually to the lean operations principles.